Hi everyone. In this video, I will explain one-dimensional linear regression. In general, linear regression is supervised learning task. Supervised learning tasks are characterized by a pair of data given to us. The first component of the pair introduces the inputs, and the second component of the pair introduces the outputs. So I will use the advantage of simplicity of this example to introduce and illustrate key concepts of the supervised machine learning task. So we start off inputting necessary libraries and also creating some auxiliary class to draw 3D arrows. Next, we will create our data. First, we create our ideal data by using linear function with slope 5 and intercept 3. This is our straight line. Next, we will generate some noise and add the noise to the original straight line. So this way we are getting noisy data, and this noisy data we will use as desired output, and the desired input will be x values for our input variable. How can we now characterize the difference or the error between the noisy yellow line and the ideal straight blue line? So for this, we can take a difference between each point, and we show it with vertical black lines for each data point. So now the question is, if we can use this error information to come up with a way how to approximate the noisy data with a straight line without knowing ideal line and its parameters. For this purpose, we will use mean squared error, which is a cost function. So cost function is a technical term. This means a method to measure the performance of machine learning model. Cost function quantifies the error between predicted and expected values and presents the error in the form of a single real number. So mean squared error fully satisfies this definition. In order to compute mean squared error, we will compute error between each value of the data. In our case, this is y noise, and the predicted value, which is the output of the linear function, which we parameterize by w multiplied by x plus intercept p. And we will do it for each data point. Now let's compute mean squared error. First, I will compute it using the for loop, just going through each data point one by one and summing and squared errors. There is, however, many other ways to do it. One of more simple and neat way of doing that is to use a dot product. So first we will define error, and we will apply the dot product to normalize it with the number of samples. As you can see, both these values match. For now, for machine learning task, we are usually given y's and x's. And our task is to estimate parameters of the approximation function. So in this case, we need to estimate w and b. So we will look at mean squared error as a function of parameter w and parameter b. So now let's draw how mean squared error looks then values of W override and B is fixed. And you can see this is a parabolic function. Now let's have a look how mean squared error looks like. Then B values the I and W value is fixed. No surprise, this is also a parabolic function because we have a second power of the error. And finally, let us have a look at mean squared error as a function of both parameters, W and B. For this, we will create the grids and compute the value of cost function at each point of the grid. So now let's confirm the shapes. So the shape of a cost function is 61 by 51. The shape of weights is 61. Shape of weights grid is 51 by 61. Shape of B is 51 and shape of B grid is 51 by 61. So we actually need to transpose value of J in order to be of the same size with W grid and B grid. And that's what we will do here while plotting in 3D space. So these blue wires, they illustrate how cost function looks in three-dimensional space. Then parameters W and B are from roughly -2 to 10 and from 0 to 10. Here I also explicitly depict 2 points. First point is a red point. This is a point which takes the fourth value of W parameter from the list of various values, and B value for the red point is the second value from B list for various values of parameter B. And finally, value of a cost function is a corresponding cost function value. And then the second point is green cross. This is actually the point where W equals 5 and B equals 3. So this point represents our ideal values for parameters, and therefore the value of a cost function here should be 0. So how are we going to travel from this point to the vicinity of optimal point? For this purpose, we will use a technique called gradient descent. So first we will compute the gradients with respect to parameter B and with respect to parameter W. And next, we will use some portion of this gradient in order to travel along the cost function surface and get the new point. Doing so, we expect a few things to happen. First of all, we expect values of gradients to decrease. Second, we expect that each next step will be shorter than previous one because the gradients are getting smaller. Finally, we expect value of cost function at each new point to decrease, and at the end of our journey, we hope to reach some close vicinity of the optimal point. We should never hit the ideal parameters, but we should converge to some vicinity of the optimal point. Now let's go back to our code. So in order to implement gradient descent, we will need to compute gradients. And for this purpose, we have to derive formulas for derivative of cost function with respect to parameter w and cost function with respect to parameter b. Derivative of cost function with respect to parameter w equals average of the following multiplication: 2 multiplied by x value multiplied by corresponding error value. Derivative of cost function with respect to parameter b is average of 2 multiplied by error. So now let's implement this. We will randomly initialize parameters w and b in order to have some values. Then we compute the predictions, the error, which is difference between predictions and the noisy data, gradient for parameter w, and gradient for parameter b. Next, I will draw the gradients in the 3D space. Because the values of the gradients are huge, I am taking only some portion of the gradients in order to visualize it in the 3D space. So next, we will update the parameters as follows. We will take a parameter and deduct a portion of a gradient from its old value and assign it to the new value. And we will do it for both parameters w and b. This portion of the gradient is called learning rate, and usually it's set to a small number. In this case, this is 0.01, but sometimes this learning rate can be much lower, or sometimes it can be 0.1. So it all depends on the algorithm and a particular optimization procedure. The reason to use this scaling parameter is to make gradient descent stable. If we provide a huge value of the gradient into this equation, the change of the parameter value also will be huge, which will cause, if you provide a huge value of a gradient into these equations, the change of the parameters will also be very big, and it will cause instability in the gradient descent algorithm. So now let's summarize what we have done. We have initialized parameters with random values. Then we computed predictions, error, and the gradients. And then we computed value updates for parameters. Now let's implement this algorithm fully. So first we initialize the parameters. Next, we will define some auxiliary variables to track change of parameter values in time. This will be w in time and b in time variables. dw in time and db in time are variables to store gradient values, and mse in time is variable to store various values of cost function. And we'll run this algorithm for 120 iterations. So in the first step, we'll compute cost function and gradient. So we compute the predictions, we compute the error, then we compute the gradients, and the cost function value, and then we record these values. On the second step, we define the learning rate and compute value of parameter W and of parameter B, and record these parameters into corresponding variables. So let's run this overview. So after 120 iterations, parameter W is 4.93 and parameter B is 3.45 and the loss functions is 862. So now let's explore convergence of the parameters, cost functions, and gradients. So as we can see, parameter W indeed converges to its true value where W equals 5. Parameter B is oscillating and gradually converging to its true value B equals 3. The loss function is decreasing in time, and gradient of parameter W is decreasing and gradually converging to 0. And similar picture happens for gradient of parameter B. Here it decreases, then slightly increases, and then converges back to 0. This is fully expected behavior. Now let us visualize the gradient descent iteration by iteration. So here I will depict evolution of parameters W, B, and corresponding cost function value throughout gradient descent. So we started initialized point and then we gradually going down to the optimal point. In the next picture, I will show it explicitly with arrows to confirm that we're actually descending at each following step to the optimal value. And finally, let us compare the original line and approximated version of it. So here you can see that the blue line, which we originally used to construct noisy data, is almost identical to the green line, which represents our prediction. And these predictions are made using parameters optimized with the help of linear regression. So let me summarize a few takeaways. So first of all, we need to select approximation function. In this case, we select approximation as a straight line. Second, we need to define a cost function, which will be our indicator of how big the error between real data and predicted values is. And then we have to apply gradient descent in order to optimize parameters of the approximation function in the space of cost function. And we expect that at each iteration, the cost function value will reduce and the gradients of parameters will also be convergent to 0. In this particular case, we also know true values of the parameters, and we can say that convergence of parameters to value 5 in case of parameter W and value 3 in case of parameter B is what we expect to see, and this is ideal state of the approximation model. However, in general case, we don't have the luxury of having true model, and we don't know the true parameters where we should converge to. So this example shows basic concepts and the basic ideas which are used throughout the supervised machine learning algorithms. So thank you very much. Stay tuned for coming videos. Hi everyone. In this video, I will explain about logistic regression and its NumPy implementation. So we will start off importing necessary libraries like NumPy, matplotlib, and also help a class to draw 3D arrows. In the previous video, I have explained linear regression. And in the case of linear regression, they used continuous numerical data to approximate with the linear equation. Unlike linear regression, logistic regression is dealing with categorical data, which means data are taking some discrete values. In this particular case, we will consider categorical variable with two different values, 0 and 1. We will refer to data points with 0 value to be the data from the negative class, and we will refer to data points with value 1 to be data points from the positive class. So let's construct this binary data. In total, we will take 15 data points, and we will assign 0 to first 7 data points, and then the remaining 8 data points will be assigned value 1. So let's create this data and visualize it. Now our task is to categorize the data points using some approximation function. Let's try to do it first with linear regression. So here is the algorithm to implement linear regression for these categorical data. And let's see the result. So we can see a straight line, which is going through both classes. And we will make a rule of thumb that once the value of this straight line is higher than 0.5, we will assign any value to positive class. But once value of this straight line is smaller than 0.5, we will assign these values to the negative class. Once we found intersection between the line y equals 0.5 and the straight line which was approximated using linear regression, we can draw a decision border on x-axis, meaning that all the values to the right of this decision border will be assigned to positive class, and all the values to the left from this decision border will be assigned to the negative class. In our case, decision border is 6.48. So this seems like a reasonable application of linear regression. However, here we use it for classification task rather than prediction or approximation of continuous values. However, there are several problems with this approach. First of all, this straight line can go far beyond the values of 0 and 1. And you can see already here that we have values more than 1 to the right and values less than 0 to the left. And the second shortcoming of this approach is that linear regression is not stable. So let's now extend our original data and add one more data point to the positive class, and let's assign x value equal 50. So let's repeat the linear regression algorithm. Okay, now we have a new straight line, which is also going through both classes. But now what happened? is the slope of this line has drastically changed. And this resulted in decision border moving from the value 6.48 in the previous case to new value 12.06. So this means, again, that all the data points to the left should be assigned to the negative class, and all the data points to the right should be assigned to positive class. And as you can see, that several data points which we know belong to positive class, they now actually marked as negative class. So this approximation introduces essential error for classification, and this is caused by instability of the linear regression. So how can we overcome these shortcomings of the approximation using straight line? Let me introduce sigmoid or logistic function. In canonical form, its equation is 1 divided by 1 plus exponent in the power of minus x. We can also introduce additional parameters w and b, which are slope and intercept. And then the generalized formula is 1 divided by 1 plus exponent in the power of minus, and then in the brackets we have wx plus b. So we actually embed this straight line into the logistic equation or sigmoid function. Let me introduce helper function, which implements sigmoid function computation. And also let me visualize the sigmoid function for different parameters. So first we will take sigmoid function as default parameters for w equal 1 and for b equal 0. And then we will take values 3 and 10 for w and b respectively. So you see how these curves are different. This proves that changing parameter w and b, we can actually fit this logistic function or sigmoid function to the data we have. Let's try to guess the good values for the parameters and use logistic regression as approximation for our binary data points. So here you can see that the decision border is very similar to the one we had for linear regression without additional outlier point. However, this logistic function or sigmoid function only takes values between 0 and 1, and it never goes beyond 1. So we can see that sigmoid function is much more stable than linear function, and that it takes values between 1 and 0. So to implement approximation of our data points with sigmoid function, we will need to implement some algorithm to tune parameters w and b. We will follow the same approach as we did for linear regression. We will use a gradient descent. However, we need to decide first which cost function or loss function we should use. In the case of linear regression, we used mean squared error cost function. So as a first step, let's try to apply mean squared error for sigmoid function as well. The formula of mean squared error in the case of sigmoid function will look like this. So we will take a squared difference between y value and the sigmoid function approximation. We sum all these squared differences across all the data points, and we divide them by n. And this will be our mean squared error. So now let's investigate how this mean squared error behaves itself. Then one of parameters, either w or b, is fixed, and we will see how the function behaves for different values of those parameters. So first, let's build profiles for various fixed values of parameter w. So this means we will derive parameter b in some range, but for parameter w, we will take a particular slices. So let's go ahead and run this. And as you can see, now we build mean squared error as a function of b for a given parameter w. So for example, in this case, w equals 5. In this case, w equals 1. In this case, w equals 2. In this case, w equals 9.5. And you can see that all these section profiles or slices, they look very differently. They look similar for similar parameter values. However, if parameter values differ a lot, they look very different as well. So this is not a good sign, actually, because in case of linear regression, we saw that we have a nice profile for any parameter value. However, in this case, we see that depending on the parameter value, the shape of the slice is changing drastically. Now let's go ahead and do the same for parameter b. So we will take multiple values of parameter b and fix it, and then vary parameter w in a particular range. So as you can see, in the case of parameter w, for different values of parameter b, the section profiles or slices, they look also quite different from each other. That's another glimpse of the problem. So why it's happening? This means that depending on the parameter value, we have to actually optimize a different function. And this is not good news for us. So to complete this investigation, let's finally build mean squared errors as a function of both parameters w and b, and see how this function looks in three-dimensional space. So you see that function is changing drastically across parameters w and b, which we have seen already using the slices, and we also can see a lot of local minima regions like this. So this means if we gather this local minima, we have a non-zero probability to stuck here, and our optimization will not really achieve the goal of optimizing the loss function very well. So also you can see there is a huge valley here, which has multiple local minima areas as well. So what is the problem? Why is that? Let's refer to linear regression case once again. So in linear regression, the MSE had a parabolic profile. And in this case, you can draw any tangent line you like, but you will never be able to draw a tangent line the way that it will split the function in two pieces. One piece of the function will lie to the left of the tangent line, and another piece of the function will lie to the right of the tangent line. And this is example of convex function. Now let's consider a different function, let's say, which behaves like this. And now we can draw a tangent line which will actually split the function by having some function values to the left of the tangent value and having other function values to the right of tangent values. So this function is called non-convex. There is more accurate mathematical definition using second-order derivatives. However, in this video, we will not go into those depths of mathematics. And this example for us is enough. So obviously you can see that mean squared error cost function for logistic regression is non-convex function. And that is exactly why we have these local minima areas. And so on. Now let's consider what could be a good alternative to mean squared error cost function for logistic regression. First, let's consider cost or loss functions. In machine learning, these two terms are used interchangeably. for positive class. Let's consider function minus log of x. So in case of minus log of x, we will have very high value of the function if logistic regression generate value close to 0. In case of 0, it will be positive infinity. However, if we generate value close to 1, then cost function will take value 0. And then in between these two edge cases, this cost function is monotonously decaying, which is also good for us. So we will take minus log of x as a cost function for positive class. So we will compute a cost function as a sum of logs of sigmoid function values divided by number of data points and taken with negative sign. So this is a general equation, and this is more precise exact mathematical equation. So now let's consider cost function for negative class. In this case, we will use function minus log of 1 minus x. What would happen is, if logistic regression is predicting value 0, then our cost will be 0, and it will be very small in the vicinity of 0. However, if we predict a value close to 1, it will increase, and at 1, this value will be exactly plus infinity. Again, between these two edge cases of 0 and 1, function is increasing monotonously, so we can think of this as a good candidate for the cost function in the case of negative class. So in the case of negative class, we will take a log of 1 minus sigmoid function value, take a sum of all these logs across the data points, divided by n, and take with negative sign. Now, let's unify these two functions, negative and for positive class, into one function or loss function for both classes. And this function is called binary cross-entropy. So what we will do, we will take a positive class function log of sigmoid and multiply it by y value. And then we will add log of minus sigmoid value multiplied by 1 minus y. So what would happen here is then yi equals 1. This component equals to 0. So the whole part for a negative class will not be computed because it turns into 0. However, then yi equals 0, this part turns into 1, and here y itself is becoming 0. So the part of a cost function for positive class will also vanish. So this is the way how we can join cost functions or losses for both classes in one formula. So let me draw the cost function in three-dimensional space. And as you can see, binary cross-entropy cost function is convex function, and it should have a local minimum, single point. So here let me provide an example how to compute binary cross-entropy loss function. So now, once we decided a loss or cost function, we should go ahead and run a gradient descent. In order to do so, we will have to get a partial derivative with respect to parameter w. In this case, partial derivative of binary cross-entropy loss function with respect to parameter w equals a sum across all the data points. And for each data point, we have to multiply value of x by corresponding difference of between sigmoid function and value. Then divide it by n and take it with negative sign. So let's compute the derivative with respect to parameter w, or gradient of parameter w. Partial derivative with respect to parameter b should be computed as follows. We should take a sum across all the data points, and for each data point we should compute difference between sigmoid function output and corresponding y value. Then divide this sum by n and take it negative sign. And these are our gradients for parameters. Finally, we should update our parameter values by using the old value of the parameter and derivative or gradient value of the parameter multiplied by the learning rate. And because we do gradient descent, we should take the difference between the old parameter value and the multiplication of learning rate and parameter gradient. And this is true for both parameters. Finally, let's run gradient descent algorithm. Start off by initializing randomly parameters w and b. Then we introduce auxiliary variables to store history of cost function of parameter w and parameter b in time, and history of gradient of w and gradient of b. However, because linear regression is highly nonlinear function, we will take 5,000 iterations. As in the case of linear regression, in the first step, we will compute the predicted value of y using sigmoid function. Then we will compute the loss value or cost function value. Then we will compute gradients for parameter w and for parameter b, and also store it in the history variables. And then in step 2, we will update values of parameter w and parameter b, and also store them in the history variables. So let's run this algorithm. And we have values for w and b, 1.55 and minus 9.92 respectively. Let's visualize the gradient descent. Because we have a huge number of epochs or iteration, we will not draw parameter values and corresponding cost function values for each of steps, but we only take parameter values on each 100th step. So let's go ahead and visualize this. So this is our gradient descent for logistic regression, where each point is shown after 100 iterations. So now let's have a look at the evolution of cost function or loss function in time. We see that loss function or cost function is decaying in time and approaching zero, and it decreases in uniform and homogeneous manner. We can also see that gradient for parameter w is convergent to zero, and gradient to parameter b is also convergent to zero. So this is expected behavior using the gradient descent optimization. And finally, let us visualize the trained model and see what result we get. So here you can see that our trained model has parameter w equals 1.553 and parameter b equals minus 9.922. Decision border in this case will be 641. Logistic regression is a very good approximation for binary class problem, and here we have implemented it using gradient descent. In the same way we have implemented linear regression, but we have changed the loss function and the corresponding gradients for the parameters. So that's it for logistic regression. I hope you like it. Please subscribe, and I see you in the next videos. Thank you.